Titan looks like the perfect backup Earth. It has air, rain, rivers, lakes, even seas under an orange sky. But behind every familiar feature is a hidden killer. Air you can't breathe, lakes you can't drink, and a distance that makes rescue impossible. In this video, we'll tear down the illusion and show why the only way to live on Titan is not to live on Titan at all. Titan looks like a place that should work, and that's exactly why it's so dangerous to think about. When people list most promising worlds for human settlement, this moon of Saturn keeps showing up near the top, as if it's quietly waiting to be our backup world. It has air, it has weather, it has rain and rivers, and even seas with names. It's not a bare rock or a killing vacuum. It sounds, at first contact, almost friendly. That first impression is wrong in ways that get worse the more closely you look. Start with scale, because scale tricks you. Titan isn't a little ice ball. With a radius of about 2,575 kilometers, roughly 1,600 miles, it's larger in diameter than Mercury and far bigger than our own moon. Your brain hears bigger than a planet and quietly upgrades Titan from moon to world. You picture continents, coastlines, weather systems wrapped around a globe. It feels big enough to hold a future. But being large is not the same as being livable. Here, size mostly amplifies the illusion. The next hook is even stronger. Titan has a thick atmosphere, not a thin whisper like Mars, not the almost nothing you find on most moons. At the surface, the pressure is about 1.5 times Earth's sea level pressure. If you stood there in the right suit, you would feel air pushing on your body, not vacuum tearing at it. No explosive decompression, no boiling saliva, no instant death from nothingness. That single fact makes Titan leap ahead of a lot of other candidates in people's minds. And this isn't just any atmosphere, it's mostly nitrogen, just like Earth's. We're used to thinking of nitrogen-rich air as normal air, the comfortable background we evolved in. So when you hear Titan's atmosphere is mostly nitrogen, it sounds like the universe is offering you a discount. Same basic main ingredient, just colder and farther away. That's the first real trap. The structure looks familiar, so you start assuming the details can be fixed. Then the surface story piles on. Thanks to the Cassini mission and the Huygens lander, we know Titan has landscapes shaped by flowing liquid. There are branching channels that look like river networks. There are dark, flat areas with shorelines that behave like seas. Some of those seas stretch for hundreds of kilometers. Huygens came down on a frozen plain scattered with rounded pebbles, likely made of water ice, smoothed and arranged by past flows. These are exactly the visual cues your brain associates with habitable worlds. Rivers, coasts, erosion, sediment. But the liquid doing all that work isn't water. It's methane and ethane at temperatures so low that water itself is as hard as rock. The rain is liquid hydrocarbon. The lakes are liquid hydrocarbon. The seas are liquid hydrocarbon. From orbit, a radar map of Titan's poles looks uncannily like shoreline maps of Earth. On the ground, every drop is chemically useless to human biology. The world is playing dress-up with the right shapes made out of the wrong stuff. Weather makes the illusion even stronger. Titan has clouds, it has wind, it has haze that glows in sunlight and thickens into a global orange blanket. There is a methane cycle that acts as a twisted parallel to Earth's water cycle. Evaporation, condensation, rainfall, runoff, lakes, and back again. If you listed the basic ingredients of a living world, air, clouds, rain, rivers, lakes, Titan ticks almost all of them. That's why in blog posts and conference talks and sci-fi novels, it keeps getting called the most Earth-like moon. Yet every time Titan rhymes with Earth, you have to ask a harder question. Similar in which way and for whom? The nitrogen is real, but there is no oxygen to breathe. The rain is real, but it's not water you can drink or use for crops. The rivers are real, but they don't carve a landscape that supports forests or soil. This is a world where the outlines are familiar, but the chemistry is pointed straight at human failure. Distance adds another layer people often ignore at first. Titan orbits Saturn, nearly 10 times farther from the Sun than Earth, around 9.5 astronomical units away. Sunlight there is about 100 times weaker than on Earth, and then Titan's thick haze strips away most of what's left before it reaches the ground. That doesn't just make the surface dim and cold, it means any future settlement starts out energy poor before you've even built a reactor or laid a solar panel. And still, Titan refuses to be dismissed. Space agencies are investing in it. NASA's Dragonfly mission is being built right now to fly through Titan's dense air on rotor blades, hopping from site to site and sampling chemistry across a frozen world. So the idea of humans following later, in bases or even small outposts, doesn't sound insane. If we can land and fly a nuclear-powered drone there, surely the step after that is just a matter of budget and time. That's where the central question has to get much more precise. The real issue is not whether a few people wrapped in technology could survive on Titan for a while. With enough shielding, power and planning, humans have survived in submarines, Antarctica, space stations and other hostile environments. The question that matters is whether Titan can ever become a place where humans actually live in any normal sense. Could a city on Titan ever depend on the outside world the way a city on Earth depends on its river, its climate, its soil and its sky? Could people open a door, step out, perhaps in light gear, and treat the landscape as part of their world instead of a permanent threat? Could a culture grow there that doesn't feel like it's trapped inside an industrial machine parked on an alien rock? Right now, all the evidence points in the opposite direction. Titan's scale and atmosphere and weather make it look like a natural home for life, but every layer you peel back reveals a deeper mismatch with what human life actually needs. The nitrogen doesn't help if you can't breathe. The lakes don't help if you can't drink. The pressure doesn't help if the temperature freezes the chemistry out of everything you try to do. So the opening move in this whole story is simple and harsh. Titan is not asking whether we can visit, it is asking whether we understand the difference between surviving inside a machine on a hostile world and truly living on a world that works with us. In the next step, we'll push the temptation even harder and see why, for a moment, Titan can look easier than Mars before the betrayal starts. Titan sounds safe long before you look at a single number. The moment you hear thick atmosphere, rain, lakes, rivers, a part of your brain relaxes. Compared to the dead, black emptiness around most moons, Titan feels like an exception, like a place where nature has already done half the work for us. That feeling is powerful and it's wrong. Start with the air. On the surface of Titan, the pressure is about 1.5 bars. In plain language, that's roughly 50% higher than the air pressing on you right now at sea level. For a human used to hearing about vacuum, explosive decompression, and spacesuits ballooning like overfilled bags, that sounds almost gentle. This is not a place where your blood boils or your lungs collapse. It's more like being a few meters underwater in a swimming pool than standing on the moon. That one fact makes Titan feel protective. On Mars, the atmosphere is so thin that if you crack your suit, you're in instant lethal trouble. On Titan, the same phrase, "it has an atmosphere," carries a totally different emotional weight. It suggests that maybe, just maybe, you could walk around in something lighter. Not the huge, rigid, overbuilt armor you see in moon mission photos, but some future, sleeker gear. It's an image of air you can stand inside instead of void you must fight. Then the surface details start to stack up. When the Huygens probe dropped through Titan's sky, it didn't slam into bare rock or sink into soft dust. It landed on a frozen plain scattered with rounded stones, probably made of water ice, shaped and moved by flowing liquid in the past. Cassini's radar saw branching drainage channels carved into the ground, leading down into darker, flat regions with clean edges that look exactly like shorelines. It's not a flat dead sheet of ice, it's a landscape that's been worked on by weather. That's a huge mental shift. When we think frozen moon, we expect something static. Cracked maybe, but lifeless. Instead, Titan gives you river valleys and basins, the fingerprints of a hydrologic system. Huygens didn't just show a cold surface, Jay. It showed a cold surface that has been rained on, eroded, and reshaped. Your brain knows what usually comes with that. Fertile deltas, coasts, fish, ships, ports, eventually cities. And those dark basins near the poles? They aren't just vague splotches. They are full seas of liquid hydrocarbons, methane and ethane pooled up in depressions hundreds of kilometers across. We've mapped them, we've named them Kraken Mare, Ligia Mare, Punga Mare. You can talk about sailing on Kraken Mare or setting a base near its shore, the same way you might talk about settling by the Pacific or the Mediterranean. Names and coastlines make Titan feel less like a science target and more like a future address. But the attraction isn't only in the maps, it's in the sky above those maps. Titan has a real working meteorology. There are clouds made of hydrocarbons. There are hazes high up that thicken into that famous orange glow. Winds shape enormous dunes that wrap around the equator, tens of kilometers long and up to 100 meters tall, made of organic particles, not quartz sand. Rain falls, collects, runs downhill through channels and refills lakes and seas. The whole methane cycle plays the same role there that the water cycle plays on Earth. Almost every visual category our minds connect with habitable exists on Titan. Air you could feel on your face, clouds drifting overhead, storms forming and fading, rivers cutting through terrain, seas with inlets and bays, dunes marching across plains. If you stripped away the chemistry and just keep the shapes, you would swear you're looking at a young, weird but promising Earth. This is exactly why Titan keeps popping up in habitability discussions, even among people who know better. It appears to solve problems that kill most other destinations right away. No vacuum, no constant radiation storm at the surface, no completely barren, rock-only chemistry. And unlike Europa or Enceladus, you don't have to drill through tens of kilometers of ice to reach something interesting. Titan puts its complexity right on the surface where you can stand. Now, bring Mars into the comparison, because that's where the attraction reaches its peak. Mars has sunlight. Mars has much shorter travel times. Mars has mission windows that open regularly. But Mars has a whisper of an atmosphere, less than 1% of Earth's surface pressure. You cannot stand outside there without a fully pressurized suit. Any habitat is a balloon fighting hard against a near vacuum. One good leak is a disaster. Titan flips that. The pressure outside is close enough to Earth that structures don't have to fight as violently to stay intact. You aren't holding a fragile bubble against emptiness. You're nestled in a thick, insulating blanket of nitrogen and methane. For engineers, that sounds like an advantage. For anyone who has watched Mars mission videos, it sounds like a relief. So the simple story forms: Mars has light but no air. Titan has air but less light. Mars is dry and dust-blasted. Titan has lakes and rain. Mars is closer and harsh. Titan is farther and softer. Stand back far enough and the trade-off looks almost fair. If we're thinking long-term, if we're thinking about the deep future of human expansion, Titan starts to look like the patient, stable option. Fewer dust storms, no global radiation crisis, plenty of raw material in all that methane and all that ice. That is the trap tightening. Because all of those comforting facts are technically true, but the way we instinctively read them is wrong. We hear air and secretly translate it to breathable. We hear rain and translate it to water. We hear seas and think oceans you could sail and fish. We hear weather and think seasons humans can adapt to. Titan uses the same words, but not one of them means what it means on Earth. And here's the turning point that sets up everything that follows. An atmosphere can feel thick, sound protective, and still be completely useless to your lungs. Lakes can look like oceans and still be poisonous. A world can copy almost every shape of habitability while denying the substance. In the next step, that comfortable phrase, Titan has air, is going to break apart and the first real betrayal will show up. The atmosphere that seems to welcome you is one you can never actually use. Titan's biggest promise turns out to be its first lie. You hear thick atmosphere, you relax, and without even noticing, you swap in another word: air. But on Titan, those two words do not mean the same thing. You can stand in that atmosphere, but you can never breathe it. The sky above you would press on your skin like a protective blanket and still kill you in a single breath. Here's the core chemistry, in simple terms. Titan's atmosphere is roughly 95% nitrogen and about 5% methane, with a little hydrogen and a soup of complex organic molecules floating around as haze. Oxygen, the thing your body needs every moment to stay alive, is essentially missing. Not low, not thin, absent. Scientists call that kind of environment anoxic, which just means without oxygen. For humans, anoxic is a polite way of saying asphyxiation by default. Nitrogen itself is not the villain here. You live in nitrogen right now. About 4 out of every 5 molecules you breathe on Earth are nitrogen. The difference is that here, there's also enough oxygen mixed in for your blood to grab onto and use. On Titan, the mix never gives you that second ingredient. If you took off your helmet and tried to inhale that thick orange air, your lungs would fill, your chest would rise, and your brain would still start dying in seconds. The pressure feels friendly, the chemistry is not. Now add methane to the picture. Methane is a simple hydrocarbon, one carbon atom bonded to 4 hydrogens. On Earth, we think of it as fuel, natural gas, something you burn in a stove or a power plant. On Titan, methane is part of the sky itself. It shapes the weather, feeds the lakes and seas, and builds that entire exotic methane cycle that looks so much like our water cycle. It changes the whole character of the world, but it does nothing for your lungs. In fact, for your body, Titan's methane is just another suffocating gas. You can't breathe it. You can't metabolize it directly. It doesn't walk into your cells and help them run. Its real power is at the planetary scale, not the biological one. It lets Titan have clouds, rain, rivers, and lakes. It lets Titan carve valleys and build up seas that look so familiar from orbit. But in terms of human life support, that same methane is useless without something else we absolutely do not have in the open air there. Free oxygen. That's where the second betrayal comes in. And it's not just about breathing. On Earth, oxygen saturates the atmosphere. That's why you can light a match and expect it to burn. Fire in the simple sense is fuel plus oxidizer, usually oxygen, combining and releasing energy. Everything from cooking to metalworking to most traditional industry is assumed that the oxidizer is free. All around us, we only bring the fuel. On Titan, that relationship is flipped. The atmosphere and the lakes carry the fuel in the form of methane and other organics. The oxidizer doesn't exist in the open environment at all. There is no background oxygen to catch a spark. If you want fire in any form, an engine, a furnace, a boiler, a torch, you have to manufacture the oxygen first, store it, and then carefully mix it with all that local fuel. The sky looks thick and rich, but chemically it has removed open flame from the world. That sounds like a small technical detail until you trace it through a colony. No oxygen in the air means no simple combustion. No simple combustion means no cheap, easy heat sources that just pull oxygen from the atmosphere. It means metallurgy changes, welding changes, many standard industrial processes change. You're no longer a civilization sitting inside a free oxidizing bath. You're a machine town that must treat oxygen itself as precious inventory. This is where we have to draw a hard line between 2 questions that usually get blurred together. One is, can a person stand in this environment without being crushed or boiled or torn apart? Titan does well there. The pressure is close enough to Earth so that your body doesn't have to fight a vacuum. The other question is, can a person live by trading matter and energy with this environment, the way we do on Earth? Titan fails almost completely. On Titan, you do not step outside and breathe in something useful. You do not burn local air in an engine. You do not let crops drink rain that fell from the sky. You do not open a window because the outside is comfortable enough for a quick exchange. Every interaction with the environment has to go through filters, tanks, heaters, and machines. The atmosphere has weight, but it has no generosity. So even with that comforting 1.5 bar pressure, every human step outside still needs a closed loop. You need a suit or a vehicle that brings its own oxygen, maintains its own temperature, scrubs your carbon dioxide, keeps your exhaled water from freezing in valves and hoses, and seals every joint against gases that cannot support you. The fact that the outside won't rip you apart just changes the design of the armour. It doesn't let you take it off. And inside habitats, the story is the same. The walls don't have to hold back hard vacuum, which helps, but they still divide two totally different chemical worlds. Inside, a fragile bubble of Earth-like air. Outside, a dense, anoxic, cryogenic mix that offers you nothing your body can use directly. You're not just adding comfort to an already friendly place. You're building a small artificial planet inside a hostile one. This is the first clean break with the fantasy many people carry about Titan. The pictures of hazy skies and gentle light suggest a place where maybe you just need an oxygen mask and a warm coat. That image dies here. Titan is not shirt sleeve with a breathing pack. It is full life support from the first second to the last, for every breath, for every heartbeat. The atmosphere protects you from space, but only your machinery protects you from the atmosphere. And that leads directly to the next, even harsher step. You might be thinking, fine, so we bring our own oxygen. We've done closed life support on space stations. Maybe we can handle that. But there's a deeper barrier waiting underneath all of this chemistry. Even if you had a perfect oxygen system, even if every breath was handled flawlessly by technology, Titan would still be lethally wrong in another way that's harder to fix than pressure and air mix. The entire world outside sits at a temperature so low that normal human chemistry and engineering start to break. The betrayal of the atmosphere is just the beginning. Next comes the cold. The single number that ruins almost every hopeful thought about Titan is 94. Not 94 years, not 94%, 94 kelvins. That's Titan's average surface temperature, about minus 179 degrees Celsius or minus 290 degrees Fahrenheit. This is not just very cold in any sense you've ever felt. This is deep cryogenic cold, the kind used in labs and industrial plants to freeze chemicals solid and slow reactions to a crawl. On Titan, that's not an experiment. That's the background of reality all the time. At 94 kelvins, the everyday categories we use on Earth, solid, liquid, gas, get reassigned. Water, the thing your body is mostly made of, is not a liquid there. It's not even ice in the way you think of ice in your freezer. It behaves like rock. Hard, structural rock. NASA scientists describe Titan's surface as made of water ice that is as rigid as granite at those temperatures. When we talk about bedrock on Titan, we are literally talking about frozen water acting as geology. That inversion is brutal. On Earth, water is the universal solvent of life. It flows, it seeps, it carries nutrients, it shapes soil, it fills cells. On Titan, that same molecule is locked into the role of crust and mountain. The thing humans need most is not just unavailable, it has been reassigned to be part of the planet's skeleton. You are standing on frozen drinking water that you cannot access without mining it like ore and then spending precious energy just to melt it. And it's not just biology that hits a wall here. Human biochemistry evolved in a narrow temperature band where water stays liquid and reactions can run fast enough to support life. Your enzymes, your cell membranes, your blood, everything in you assumes a warm, watery environment. Titan's 94 Kelvin surface is so far below that band that cold almost stops being a useful word. If your unprotected skin were exposed, it wouldn't just feel freezing. Moisture would lock up. Tissues would go solid. You're dealing with conditions where the chemistry needed for life simply cannot operate in the open. But the problem spreads way beyond your body. Every system you build has its own comfort zone, and Titan sits far below most of them. Pipes that would carry water or air want to clog with ice. Seals stiffen. Gaskets shrink and crack. Lubricants thicken or freeze entirely. Plastics that are flexible at room temperature lose their give and start to snap under stress. Metals can become more brittle. Electronics packaging has to handle extreme temperature differences between warm interiors and a world outside that's barely above absolute zero. Think about something as simple as plumbing. On Earth, keeping water flowing through pipes in a winter climate is a challenge, but it's familiar. On Titan, any pipe that isn't aggressively heated and insulated end-to-end turns into a frozen plug. Every exposed valve or joint is a risk point. A short power loss isn't just uncomfortable, it's a threat to the physical integrity of your systems. Warm water that meets the outside world doesn't just cool down a bit, it wants to solidify into structural ice. This is why Titan cannot be treated as just a colder version of Earth. The world outside a habitat isn't bad weather you dress for. It's a cryogenic environment designed by physics to shut down almost everything we think of as normal chemistry. Air mixtures, liquid fuels, foods, medicines, all of them are built for temperatures hundreds of degrees warmer than Titan's surface. Every meter you extend from a habitat, every cable, pipe, joint and sensor has to be designed like equipment for a high-end lab freezer, not for a winter city. And it doesn't stop at hardware. Even your backup systems are under attack from the cold. Batteries lose performance at low temperatures. Moving parts seize, hydraulic fluids become syrup. Every layer of redundancy you try to add has to be kept in its own artificial temperature bubble. You aren't building a single warm room in a chilly world. You're building a web of heated, protected bubbles trying to do complex work in a universe that wants everything frozen and still. So when people say we can handle cold, we live in Antarctica, they are missing the scale of the problem. Antarctica's air hovers tens of degrees below freezing, not almost 200 degrees. Sea ice sits just under 0 Celsius. Engineers there fight frost and ice buildup, but the environment is still in the same basic chemical regime as the rest of Earth. On Titan, the baseline is so far removed from that regime that cold weather engineering becomes cryogenic survival engineering across the entire planet. This is the crucial shift. Titan is not just hostile to unprotected humans, it is hostile to ordinary Earth normal chemistry itself. The environment doesn't just resist your body, it resists your tools, your materials, your factories, your farms, your entire way of turning matter and energy into a civilization. You could, in theory, build layers of technology to fight this. Heating everything, insulating everything, sealing everything. But now you're not living in a climate. You're living inside a machine that's fighting the climate every second. At this point, you might reach for the one parameter on Titan that still sounds kind, the pressure. If the temperature is so lethal, maybe the gentle 1.5 bar atmosphere gives humans a real edge. Maybe you think, at least we don't have to build structures that fight a violent pressure difference the way we do on Mars or the Moon. Maybe that one thing truly makes life simpler. That hope is the next thing that has to break. Because even where Titan seems to meet us halfway, it doesn't. The pressure outside might feel close to home, but it does not buy you what you think it buys. You still need full life support. You still need heavy thermal protection. You still need armor, not against vacuum this time, but against a world that is chemically wrong and cryogenically cold. The question, does Titan's air save us, is already answered. The next question is, does Titan's pressure save us? And the answer, again, is not what most people expect. Titan's pressure sounds like mercy until you unpack what it actually gives you. Hearing that the surface atmosphere is about 1.5 bar, roughly like being a few meters underwater in a swimming pool on Earth, your brain immediately relaxes. You picture your body not fighting a vacuum, not swelling, not boiling, just existing. Compared to the Moon or Mars, where a torn suit means instant explosive decompression, Titan feels strangely humane. That comparison is exactly why so many people talk about lighter suits and thinner walls there. If the outside is already pressurized, maybe we don't need the same bulky, rigid shells. Maybe we can swap space armor for something closer to heavy cold weather gear. It sounds like Titan finally hands us a straightforward win, one fundamental problem solved by nature before we arrive. But that pressure only answers one narrow question. Will the outside air physically crush or tear a human body apart? On Titan, the answer is no. It will hold you very gently. Every other question that actually matters for living stays brutal. What are you breathing? How warm are you? What's happening to your skin, your eyes, your lungs at minus 179 degrees Celsius in a nitrogen-methane mix? Is the gas around you safe to inhale? On those fronts, Titan offers nothing. This is where the difference between pressurized and habitable really explodes. NASA's human system standards exist because putting air around a person is not enough. You need the right total pressure, the right fraction of oxygen, tight control of toxic gases, safe humidity, temperature in a narrow band, even the right levels of carbon dioxide and trace compounds. Only then does air become breathable environment. Titan gives you pressure and skips the rest. So yes, your habitat on Titan doesn't have to push as hard outward as one on Mars. The pressure difference between inside and outside is smaller. Structurally, your walls might not be as stressed. That is a real but limited engineering advantage. At the same time, the suit problem actually gets worse in other dimensions. Outside isn't vacuum, but it's still deadly. You're not just designing for pressure, you're designing for chemistry and temperature that want to end you on contact. Look at what a Titan suit really has to do. Has to keep you warm when the world around you sits at 94 kelvins. That means layers of insulation thick enough to hold a miniature summer around your body. It has to bring its own oxygen and keep Titan's nitrogen-methane mix out of your lungs completely. Because inhaling that dense, freezing gas, even for a moment, would be catastrophic. It has to handle exhaled water vapor and carbon dioxide without letting them freeze in valves and filters. Every joint, every seam has to stay flexible and sealed in extreme cold. The paradox is simple. The gentler pressure outside lets you relax one part of the suit, but the cryogenic cold and alien chemistry force you to overbuild everything else. You might not need a rigid balloon-like pressure garment, but you absolutely need a heavy thermal armor wrapped in a chemically protective shell, with a full life support backpack. What you save in structural strength you pay back and more in heating, insulation, and complexity. And the environment itself is actively dangerous in ways that don't show up in pretty images. Expose unprotected skin, and you're talking instant, deep frostbite. The air is so cold it will pull heat out of you with terrifying speed. Any contact with liquids on the surface, those methane and ethane lakes, would be even worse. They're far below the freezing point of any tissue or material we normally think of as cold tolerant. Just standing there without protection is not an option, no matter how familiar 1.5 bar sounds. Breathing is its own lethal failure mode. Drop your helmet seal and your chest will still fill easily because the outside air is dense. That actually makes it more dangerous than vacuum in one way. There's something to inhale. What you pull into your lungs is a bitterly cold, oxygen-free mix that can't support your blood chemistry. You don't choke because there's nothing there. You choke because you've inhaled the wrong thing. The friendly pressure hides a suffocating sky. So that dream of Titan as shirt sleeve with an oxygen mask dies right here. You cannot just bundle up in some insulated jacket, strap on a tank and stroll by the shore of Kraken Mare. If your face is exposed, you freeze. If your lungs are exposed, you suffocate. If your gear lets any of that gas leak into warm spaces, you risk condensation, freezing, and possibly dangerous mixtures with stored oxidizer. Every minute outdoors still requires a full integrated survival system. The silhouette of the suit might look different from a lunar one, but the dependence on technology is total. Inside habitats, the pressure kindness also turns out to be surprisingly limited. Yes, thinner walls are easier to build, but the real load your structures carry isn't just mechanical anymore. It's thermal and chemical. They have to separate a small Earth-like bubble, warm, wet, oxygen-rich, from a vast external volume that is cold, dry, oxygen-free, and saturated with methane and nitrogen. Any breach isn't just a pressure leak, it's a heat leak and a contamination event in a place where repair crews have to work in the exact same hostile conditions you're trying to escape. So when people list Titan's advantages and put near-Earth pressure at the top, they're not wrong on the fact. They're wrong on what it buys you. It does not turn Titan into an open, maybe manageable environment. It just changes the engineering shape of the prison cell. You still live behind walls, you still wear armor outside, you still depend on machinery for every breath and every heartbeat. And once you see it that way, as a prison built out of habitats, pipes, heaters, scrubbers, and suits, the next hard question arrives on its own. If every degree of warmth and every breath of usable air has to come from machines, then the real currency of life on Titan isn't land or water or even raw materials. It's power. Without massive, continuous energy, all of those protective systems fail together. The pressure won't save you, the lakes won't save you, only energy will. And on Titan, that is exactly what the universe has made hardest to get. Every problem on Titan quietly collapses into one word: power. Once you accept that humans there live inside machines, not in the landscape, the question stops being, is there air, or is there water, and becomes, can we keep the machines running forever? And right where we need abundance, Titan is starving. It's not just cold, it's energy poor in a way that turns habitability into a constant emergency. Start with distance. Titan orbits Saturn, about 9.5 astronomical units from the Sun. That means the sunlight arriving at the Saturn system is roughly 1% as strong as the sunlight that hits Earth. Not a little dimmer, about 100 times fainter. If you took a solar panel that works beautifully here and moved it out to Titan, it would instantly produce only about 1/100th of the power before you even think about what the atmosphere does to that light. And the atmosphere does a lot. Titan's sky is full of thick orange haze, layers of tiny particles and complex organic molecules that scatter and absorb sunlight. By the time the light fights through that haze to the surface, you're left with perhaps 10% of that already tiny 1%. Put those together and you're down around 1,000th of Earth's surface sunlight. Stand on Titan at noon and it feels like permanent late twilight even when the sun is technically up. On paper, you can still draw solar panels over Titan's hills and say, look, there's some power. But the numbers are cruel. To match the output of a modest solar farm on Earth, you'd need arrays hundreds or thousands of times bigger on Titan, sitting in bitter cold under a dim red disk of a sun, with haze constantly filtering the light. Every kilowatt hour becomes expensive in area, in materials and in maintenance. Solar doesn't disappear, but it stops being your backbone. NASA's own choices underline this. The Dragonfly Rotork craft that's being built to explore Titan is not solar-powered. It carries a nuclear power source, an MMRTG, because Titan's sunlight is simply too weak and too unreliable for a flying science lab that has to work for years. If a single robotic vehicle can't count on the sun there, a city certainly can't. Any serious talk of humans on Titan has to start with something else. Nuclear reactors, chemical plants, maybe exotic schemes using wind or methane flows. But all of those needed an initial energy investment and a constant oversight. And remember, on Titan, keeping the lights on is the easy part. The hard part is keeping everything warm enough to function at all. Every cubic meter of habitat air has to be heated from about 94 kelvins up to something humans can stand around 290 kelvins. That's a jump of nearly 200 degrees Celsius. Every wall, every pipe, every greenhouse, every workshop is fighting that gradient every second. You're not just powering devices, you're holding back the entire universe outside that wants to drag your temperature down to cryogenic night. On Mars, brutal as it is, sunlight can at least help a little. Solar arrays work, transparent structures can trap some heat. On Titan, the outside world doesn't just fail to help, it actively punishes you. A warm habitat leaks energy into the cold at a relentless rate. Any loss of heating isn't a comfort problem, it's a countdown. Pipes freeze, water in tanks begins to solidify, electronics drift out of spec. Life support systems designed to keep air breathable and water flowing are themselves at risk from the cold they're supposed to protect you from. That turns energy from a convenience into a strict survival budget. You need power for lighting, communications, vehicles, manufacturing, medicine, computing, and all the usual things a high-tech outpost uses. But before any of that, you have to pay the heating bill. Heat first, everything else second. If you don't have enough, you don't just cut back on industry. You start losing the layers of protection that keep Titan's environment on the other side of the wall. And the margin for error is tiny. A city on Earth can lose power in one district and struggle, but outside air and temperature still sit inside human ranges. Neighbours can bring help. On Titan, a major power failure is a compound event. Habitats cool, water in pipes and tanks locks up, some materials shrink and crack. Batteries perform worse in the cold just when you need them most. If the outage lasts too long, you aren't just rebooting systems afterwards, you're digging your way out from under frozen infrastructure. This is what energetically impoverished really means in practice. Titan doesn't just make power harder to collect, it makes the consequences of any power shortfall far more deadly. There is no coasting, No safe, idle state where you can just wait things out with a blanket and some canned food. The machines that keep you alive demand energy every minute of every day, and if you fall behind, the environment doesn't forgive you. So when people look at charts and say, we'll just bring reactors, we'll be fine, they're underestimating the scale of the dependency. Reactors too need maintenance, spare parts, fuel cycles, human expertise. All of that sits at the end of a supply chain that stretches almost 1.5 billion kilometers. Titan can, in theory, support power systems, but it cannot make them easy. And on a world where every breath, every sip of liquid water, and every degree of warmth depends on those systems, not easy becomes potentially catastrophic. By now, a pattern is forming. Titan keeps handing us things that look like advantages, and then quietly tying them to deeper costs. It has an atmosphere, but no oxygen. It has lakes, but they freeze your chemistry. It has pressure, but no comfort. It has raw materials and maybe some niche energy sources, but they all sit behind a high, constant power bill. And we're still not done. Because even if you somehow solve the energy problem with big reactors and clever engineering, Titan takes away something much older and simpler than solar panels: fire. The world is soaked in fuel, but the sky refuses to give you the oxidizer to burn it. The next step in this argument goes right there, into a world where combustion, the basic trick human civilization has used for thousands of years, stops working in the open air. Titan looks like an energy jackpot until you remember how fire actually works. Everywhere you point, there's carbon chemistry, methane in the air, methane and ethane pooled in lakes and seas, dunes made of organic particles, haze built from complex hydrocarbons. It feels like standing on top of a giant fuel depot. Your instinct is, okay, sunlight is weak, but who cares? We're literally sitting in fuel. That instinct is wrong in a very specific, very dangerous way. Combustion is not just have fuel, get energy. It's a partnership between fuel and oxidizer. On Earth, that oxidizer is almost always oxygen from the air. You bring the fuel, wood, coal, gas, oil, and the atmosphere donates the oxygen for free. Light a match and you're dipping into an ocean of ready-made oxidizer that costs you nothing. Fire as we know it depends on that background gift. Titan deletes that gift. Its atmosphere is mostly nitrogen, with a few percent methane and other trace gases, and essentially no free oxygen. The lakes and seas are mostly liquid methane and ethane. So yes, you are surrounded by fuel, in the sky, in the lakes, in the soils and dunes. But the other half of the equation is missing everywhere outside your habitat walls. There is nothing in the open environment that will join with that fuel in a sustained burn. The result is a kind of chemical paradox. Titan is loaded with energy and potential form, but you can't just strike a spark and tap it. Any engine, furnace, boiler or rocket that runs on burning something has to bring its own oxygen along for the ride. Every flame becomes a controlled reaction between locally harvested fuel and oxidizer that you had to manufacture, store, and protect inside your settlement first. That shift turns oxygen from background into inventory. On Earth, we never think about where to get oxidizer, because the answer is always all around you for free. On Titan, oxidizer production becomes a major industrial job. The most obvious source is water ice in the crust. You mine it like rock, haul it into warm facilities, melt it, and then use energy to split it into hydrogen and oxygen. Only then do you have something that can combine with all that handy methane to release useful energy. But notice the loop you've just closed. You need power to make oxygen so that you can burn methane to get power. If the energy you spend splitting water isn't much less than the energy you get back from burning the resulting oxygen with local fuel, you're just running into a place. What looked like an energy paradise when you saw all those dark hydrocarbon seas is, in practice, a complex processing chain built on top of an already fragile power system. And even after you've done the work, oxygen doesn't behave like air on Titan. It's not something you treat casually. It's a concentrated chemical you have to store in tanks, move through pipes, regulate carefully near flammable organics, and keep from freezing or overpressurizing in an environment that wants to swing everything toward cryogenic. Every kilogram of oxidizer is something you either shipped across billions of kilometers or wrung out of ice at a high energy cost. Here's the deeper contradiction. The reason Titan is so chemically rich, so interesting to scientists, is exactly the reason it's so bad for our kind of industry. That anoxic atmosphere, the one that refuses to give you oxygen to breathe or burn, is what allows complex organic molecules to accumulate instead of being oxidized away. Titan is a fantastic laboratory for prebiotic chemistry, for studying how carbon compounds behave before life and oxygen take over. But that same chemistry is hostile to a civilization built on fire and rust and easy oxidation. Think about how many parts of human technology have fire at their core. Engines that burn fuel and air, furnaces that melt and shape metal, simple heaters, incinerators, kilns. Even if we move beyond open flame, a lot of our heritage systems assume an oxidizing atmosphere that participates in corrosion, combustion, and countless industrial reactions. On Titan, the air never takes that role. It sits there, cold and indifferent, while you import every reactive molecule from inside your pressure domes. So the question stops being, is there chemical energy on Titan? Of course there is. There's plenty of stored energy in those hydrocarbons. The real question is, how hard is it to turn that into practical energy at scale day after day for a city? And the answer is, much harder than on Earth. Because every step requires infrastructure that itself hangs off a fragile power grid and supply chain. In the end, you're left with a stark picture. Titan has matter, but not easy metabolism. It has carbon, but not free fire. It has seas of fuel, but no natural way to ignite them without building an entire oxidizer industry first. Human civilization, as we've practiced it for thousands of years, is a story of lighting things on fire. Wood, coal, gas, oil, and riding the heat. Titan quietly ends that story the moment you step outside. That pushes the problem down another layer. If the air, the light, and even the basic chemistry around you refuse to cooperate, maybe the hope shifts to the ground itself. Maybe you think the surface is at least made of familiar stuff we can build with. But Titan has one more inversion waiting. Even the rock under your feet is something you need for life, trapped in a form you can't use. The landscape looks solid and reassuring, and that again is part of the deception. Solid ground on Titan looks like comfort until you learn what it's made of. We're used to thinking of rock as rock, silicates, basalt, granite, the hard mineral stuff that makes up continents and mountains. On Titan, that role is played mostly by something else entirely: water. At 94 kelvins, water doesn't just freeze, it locks into a rigidity where it behaves like stone. The crust under your boots is, in a very real sense, frozen drinking water pretending to be bedrock. When Huygens dropped through Titan's atmosphere and finally hit the surface, it didn't splash and it didn't disappear into powder. It came to rest on a frozen plain scattered with rounded pebbles and blocks, likely made of water ice that had been shaped and moved by flowing liquid in the past. To your eyes, that terrain would look strangely familiar. Stones, a hard floor, maybe a sense of standing in a dried riverbed. The familiarity is fake. The chemistry is upside down. The substance that carries life on Earth is here doing the job of granite. That inversion matters because it changes where your basic resources are hiding. On Earth, if you want water, you dig for it as a fluid or a soft solid. Wells, aquifers, snow ice, you can melt with modest heat. Rock is what you build on. On Titan, those roles swap. The rock is your water. To get liquid, usable H2O, you're not lifting something from a river. You're mining it out of structural material, hauling chunks of crust into processing facilities and dumping energy into them just to bring them out of the temperature regime of stone. Move away from that landing site and the strangeness keeps building. Cassini's radar images revealed vast dark bands wrapped around Titan's equatorial regions. Look more closely and those bands aren't lava flows or seas, they're dunes. Giant dune fields, with individual ridges 1 to 2 kilometers wide, stretching for hundreds of kilometers and standing roughly 100 meters high. On Earth, dunes mean sand, and sand usually means quartz or other silicate grains slowly ground down from rock. On Titan, those dunes are made not from silicate sand, but from organic or hydrocarbon-coated particles. Tiny grains and clumps of carbon-rich solids born from atmospheric chemistry and surface processes, piled up into long parallel ridges by slow winds. If you walked there in a suit, the ground beneath your boots would not be the familiar mineral crunch of a desert. It would be some foreign mix of frozen organics and ice, responding to pressure and movement in ways our civil engineers have almost no experience with. For settlement, that combination, ice bedrock, organic dunes, isn't just a fun fact. It's a deep practical problem. Everything we take for granted in building a city assumes certain materials with certain behaviours. We anchor foundations into rock that doesn't creep at our temperatures. We pour concrete. We manage dust that behaves like silicate dust, with known friction and cohesion patterns. We know how asphalt responds to load, how steel expands and contracts, how soils settle over time in 1G gravity. Swap the entire material palette for cryogenic water ice geology under Titan's weak gravity, about 0.14 G, and the playbook goes out the window. Anchoring a structure into ice that is hard as rock at 94 Kelvin might seem easy, until you start dumping waste heat into it and find that warmed regions form differently, or refreeze with the internal stresses. Road building across organic dunes means your soil is chemically reactive in unfamiliar ways and may become brittle or strangely sticky at different temperatures. Seals and footings that work beautifully on basalt might start sliding or cracking when mated to ice rock. Dust and fine grains create a different class of headaches. On the Moon and Mars, dust is razor-edged silicate that clings electrostatically and chews through seals and joints. On Titan, the fine particles are mostly organic. That sounds softer, safer more, until you remember that these are complex hydrocarbons in a cryogenic, methane-rich environment. They may cake, absorb, fracture, or electrostatically cling in unexpected ways. Every hinge, airlock, and sensor you expose has to be tested against this alien sediment, not just sterilized lunar regolith. Even basic choices like, do we build above ground or dig in, become messy. Burrowing into the Titan's crust means cutting tunnels through rock-hard ice. Traditional excavation tools, drills, explosives, heavy equipment must be re-engineered for a medium that can crack unpredictably if warmed, shatter if stressed while too cold, and may sit above layers of softer or more ductile ice. You're not applying known mining techniques in a new place. You're inventing an entirely new branch of cryogenic civil engineering in the dark. All of this feeds into a larger truth. Solid ground is not the same as usable ground. Titan absolutely has terrains you can stand on, hills you can map, dunes you can cross, and shores you can trace on a chart. But from a human point of view, the surface is materially misaligned with what we need. The thing that looks like safe rock is actually the life support fluid we require, locked up and expensive to access. The stuff blowing in the wind is exotic chemistry that doesn't behave like ordinary sand. The building site you pick isn't just another patch of alien dirt. It's a test bed for structural behaviours we've never lived with. So far, Titan has taken every comforting category, air, lakes, pressure, Earth-like landscapes, and flipped its meaning. The surface is no exception. It looks right and acts wrong. That raises an obvious next question. What about the climate itself? Weather, seasons, storms, those are the things we cope with on Earth every day. Maybe you might hope Titan's meteorology is at least a familiar kind of problem. But once again, the pattern holds. Titan has rivers, clouds, and rain, and yet its sky cares nothing about human life in a much deeper way than any storm on Earth ever could. Weather on Titan looks like a promise, but it isn't a promise to us. When we see clouds and rain and rivers on another world, we instinctively translate that into maybe life could work there. On Titan, that translation fails. The sky is busy, the landscape is active, and none of that motion has anything to do with supporting human beings. Start with the part that sounds most like home. Titan has a real cycle, like our water cycle, but built from methane. Liquid methane and ethane evaporate from lakes and seas, rise into the atmosphere, form clouds, fall back as rain, collect in channels, and run downhill into larger basins. It's a complete loop. Evaporation, condensation, rainfall, runoff, storage. On Earth, that same pattern feeds rivers, fills reservoirs, waters crops, and hydrates every ecosystem we know. On Titan, the loop is closed around the wrong liquid. Methane rain does not water fields. It doesn't recharge aquifers you can tap for drinking water. It doesn't soak soil that could grow plants. It lubricates a cryogenic world, carving valleys in ice rock, refilling hydrocarbon seas, and moving carbon-rich material around a frozen landscape. From a scientist's point of view, that's thrilling. From a colonist's point of view, it's a weather system that ignores every biological need you have. Even the winds play this strange double game of familiarity and threat. When Huygens descended through Titan's atmosphere, its instruments saw something surprising. Near the ground, in the last few kilometers, winds were gentle, only a few meters per second. At the surface, you could stand there in a suit and feel just a light push of air. Nothing like a Martian dust storm or a terrestrial hurricane. It would feel eerily calm for such an alien place. But higher up, around 120 kilometers altitude, the story changed completely. There, winds screamed sideways at roughly 120 meters per second, about 430 kilometers per hour, or 270 miles per hour. That's far beyond hurricane strength on Earth, a fast, super-rotating jet of atmosphere sliding over the slower-turning body below, so Titan is meteorologically active even if the ground sometimes feels still. Above any future habitat, powerful flows of air would be constantly rearranging haze and pushing weather systems around. Then there are the seasons, and this is where Titan quietly breaks our sense of time. Titan is tidally locked to Saturn, always showing the same face to the planet it orbits, and it completes that orbit in about 15 days and 22 hours. But Saturn itself takes about 29 Earth years to go around the Sun. Because Saturn is tilted, its system has seasons, and Titan shares them. Each season, spring, summer, autumn, winter, lasts more than 7 Earth years. For a human settlement, that means climate planning on alien timescales. You're not dealing with a familiar annual rhythm of planting and harvest, wet and dry. You're dealing with long, drawn-out phases where sunlight levels, cloud patterns, and rainfall statistics shift over spans longer than many missions. Next season on Titan isn't next year, it's the next decade. That stretches everything from power planning to structural design into a strange, slow cadence that humans aren't built to feel intuitively. And again, the rain itself is the wrong kind of comfort. Methane rain falls slowly compared to Earth's downpours, thanks to low gravity and dense air, but it's still falling at temperatures that deep freeze almost every material we care about. A methane storm there doesn't feed rivers of drinkable water. It splashes cryogenic liquid across ice rock, potentially pooling around any structure unlucky enough to sit in a low spot. Your habitat walls don't just need to be waterproof, they have to resist direct contact with a solvent that can interact with seals, coatings and organics in unfamiliar ways at temperatures that already push every material to its limits. So yes, Titan has rivers. Yes, it has storms. Yes, there are seas with coastlines that shift as climate patterns move. There are changes over years and decades as different hemispheres tilt toward and away from the distant sun. There is even a kind of alien hydrology, but none of it hydrates anything alive. It just moves liquid hydrocarbons through a system that never once pauses to offer a glass of water or a growing season. The big mistake is to see motion and assume mercy. Titan has weather in the same way a machine has moving parts. The fact that clouds gather and winds blow and rain falls doesn't mean the environment is welcoming. It means the energy and chemistry of a frozen, oxygen-free world are being shuffled around in patterns we can map, but not join. Our bodies, our crops, our infrastructure are not invited into that loop. They are targets it will hit without noticing. By now, we've stripped the friendliness out of Titan's air, its temperature, its chemistry, and its ground. The sky turns out to be no better. It's dynamic, but it isn't on our side. So maybe you think there's one last environmental card Titan can play. Gravity. Low gravity is one of its most famous selling points. Easy flight, easy launches, less stress on structures. Perhaps this is finally the parameter that works for us instead of against us. That's where the story goes next, into the gravity bargain. A world where machines thrive in slow, thick air, but human bodies may quietly fall apart over time in a field that's only a fraction of Earth's. Titan finally seems to hand us something that looks like a real advantage. Gravity. For once, the numbers sound like they're on our side. On the surface, gravity is only about 1.35 meters per second squared, roughly 14% of Earth's. That's even weaker than the Moon's pull. Combine that with a thick, dense atmosphere, and suddenly a lot of engineering problems get dramatically easier. It feels like the first time Titan is actually helping. Engineers look at those conditions and light up. Low gravity means you can lift more with less. Dense air means wings and rotors work incredibly well. That combination is exactly why NASA built the Dragonfly mission the way it did. On Titan, a rotorcraft the size of a car can fly in slow, heavy air, while weighing only a fraction of what it would on Earth. Dragonfly isn't fighting for lift, it's gliding through conditions that, from a flight perspective, are almost generous. Now scale that idea up. In principle, Titan is one of the few places in the solar system where you can imagine real aircraft operations as a normal thing. Not just rockets, not just hoppers, but routine atmospheric flight. Cargo drones hauling supplies between sites. Survey craft cruising over dune seas and lake shores. Maybe even one day, crewed flyers slipping through the orange haze like slow, efficient helicopters. Compared to the brutal flight environment of Mars, Titan looks like a dream. Launch and ascent from the surface benefit too. With only about 0.14 G to fight and a thick atmosphere to lean on for aerodynamic lift, getting vehicles off the ground and into higher trajectories is mechanically simpler than on Earth. Structural loads are lower. Stresses on towers, cranes and large habitats shrink. In pure engineering terms, a lot of hardware will thank you for building it on Titan instead of under full Earth gravity. So at first glance, this is the counter-argument the optimists have been waiting for. If you can move mass easily through the air, if you can reduce structural overbuilding, if you can fly everywhere instead of crawling over hostile terrain, maybe you can start to imagine a distributed, agile settlement. Less fuel per trip, less wear and tear, more flexibility in how you connect outposts and share resources. The problem is that gravity doesn't just act on machines, it acts on bodies. And for biology, we have every reason to think that 0.14 G is not a gift at all. Decades of human spaceflight have shown what happens when gravity is reduced or removed. In microgravity, astronauts lose bone density, their muscles atrophy, their cardiovascular systems decondition, their fluid distribution shifts, and their vision and balance can change. We fight that with intense exercise and still only partially succeed. We don't actually know how much gravity is enough to keep a human body healthy over years, much less over generations. Partial gravity environments, the Moon at about 0.16 G, Mars at about 0.38 G, are still big question marks. We have hints, simulations, and short-term data, but no long-term generational experience. Titan's surface gravity is even lower than the Moon's. There is zero evidence that such a weak field would be sufficient to maintain strong bones, robust muscles, normal heart and blood vessel function, and healthy development in children. So while your machines are rejoicing, your tissues may be quietly dissolving. Joints bear less load, which sounds nice until bones adapt by weakening. Muscles lift less, so they shrink. The heart doesn't have to pump as hard against gravity, which can lead to cardiovascular changes we only partly understand. For a short mission, you might accept that and plan for rehabilitation back on Earth. For a permanent settlement, especially one where people are born and grow up on Titan, that's a completely different risk. Imagine raising a child who has never felt more than 0.14 G. Their skeleton, muscles, inner ear, circulation, all of it would develop in a regime our species has never experienced long term. How easily could they tolerate higher gravity if they ever tried to travel? Would they be locked into Titan's weak field, effectively unable to visit Earth without extreme medical support? Would even small falls become dangerous because their bones are less dense? These aren't abstract concerns, they go straight to whether living on Titan means building a trapped, physically fragile population. And it's not just the body. Motion, play, work, sports, all the ways humans intuitively learn how to move depend on gravity. In 0.14 G, walking, running, lifting and throwing all feel wrong. You can adapt, but you're adapting to a context that might quietly be damaging you in the long run. We have no proof that a society can stay healthy generation after generation in such a weak field without constant medical intervention, artificial gravity, or both. So the gravity bargain comes into focus. Titan is close to perfect for flying machines. Drones, aircraft, balloons, rotorcraft. This world is practically tailored for them. It eases the strain on the structures. It makes lifting hardware attractive. From an engineering and robotics perspective, it might be one of the best playgrounds in the solar system. But that same environment is deeply suspect as a place to grow old, to heal from injury, to carry a pregnancy, to raise children whose bones and hearts need steady, healthy loading. In other words, Titan optimizes for drones more than for people. It's a fantastic destination for robots with propellers and wings, powered by nuclear batteries, sampling lakes and dunes under a gentle pull of gravity. For human bodies, it's an untested, probably unhealthy environment that might lock settlers into permanent dependence on medical systems and perhaps rotating artificial gravity habitats just to avoid long-term breakdown. And that brings the story to a critical turning point. If the outside environment, air, ground, weather, gravity, keeps favouring machines over biology, then the logical response is clear. You stop trying to live on Titan in any open sense. You retreat almost completely into sealed, engineered habitats. Those bubbles of Earth-like conditions stop being shelters and become the only real-world humans in the Saturn system ever know. At this point, the idea of living on Titan quietly flips. You're not really talking about people adapting to a moon. You're talking about people adapting to a machine. Outside, every major environmental factor is wrong. The air, the temperature, or the chemistry, the gravity, the light. So instead of meeting Titan halfway, human life collapses inward. The habitat stops being a building and becomes, in every important sense, the planet. Think through what has to be manufactured from scratch. Breathable air doesn't exist outside, so you have to create it, mix it, purify it, and keep it moving. Temperature is nearly 200 degrees Celsius below what your body needs, so you have to raise it and hold it steady every second of every day, no matter what is happening in the power systems. Water is locked up as stone-hard ice in the crust, so you have to mine it, melt it, purify it, then keep it from freezing again in every pipe and tank. Pressure is technically there outside, but the composition is lethal, so the inside atmosphere might as well be from another universe. All of that has to run as a continuous process, not a one-time setup. Air isn't just added and forgotten, it's constantly breathed, exhaled, scrubbed of carbon dioxide, filtered of contaminants, and topped up with oxygen that has to be produced somewhere. Heat isn't just turned on in winter, it's fighting a constant, brutal gradient to the 94 Kelvin darkness beyond the walls. Water isn't just filled into a reservoir, it's circulated, used, cleaned, and recirculated, with every leak and cold spot threatening to turn it back into structural ice. That's what closed loop really means on Titan. The waste from one process becomes the feedstock for another, in a chain that can't afford many weak links. Exhaled CO2 has to be captured and either stored or broken down. Organic waste has to be treated or recycled. Trace chemicals need to be kept in balance so the air doesn't become slowly toxic. On Earth, nature handles most of this by itself, with oceans, soils, plants and atmosphere working in gigantic forgiving cycles. On Titan, nature is no help at all. The entire loop sits inside your machinery. This is where system dependency becomes terrifying. In a normal city on Earth, if one system fails, a power line, a water main, a local heating plant, other layers often cushion the blow. You can open a window, get bottled water, move to a different neighborhood, call in help from far away. On Titan, a major failure doesn't just inconvenience you, it cascades. Lose heat and walls and pipes begin to drop toward ambient. Water starts to freeze, first in exposed runs, then deeper in the network. As lines freeze, pumps strain. Batteries and electronics in cold rooms fall outside their design temperatures. If the problem isn't stopped fast, you don't just lose warmth, you start losing the very infrastructure that could bring that warmth back. A thermal failure becomes a plumbing failure, then a power failure, then an atmospheric failure. Rooms that used to be backups turn into frozen wreckage. In that sense, a Titan colony would be less like a city on land and more like a ship at sea that can never make port. Everything that keeps you alive travels with you, inside a sealed, engineered volume surrounded by a medium you cannot inhabit. On a ship, the ocean is the thing you move through, not the thing you breathe or drink without treatment. On Titan, the external world plays the same role, impressive to look at, useful for raw material, but deadly if it crosses the hull. Closed-loop life support is not science fiction anymore. Space stations have been doing versions of it for years, but the hidden catch is scale. Keeping a handful of disciplined professionals alive for months or a couple of years is a very different challenge from sustaining thousands of people indefinitely. Once you add schools, hospitals, workshops, recreation, aging populations, births, and all the messy realities of human life, redundancy and repair stop being technical details and become civilization-level tasks. For a large settlement, you don't just need spare filters and pumps. You need whole industrial chains that can produce replacements locally when shipping them from Earth becomes too slow or too rare. You need medical systems that can handle failures of both bodies and machines at the same time. You need crews trained not just to operate technology, but to rebuild it from parts when original suppliers are long gone. Titan's environment makes every one of those requirements harder. Extreme cold, distance, exotic materials, weak gravity. So the phrase living on Titan starts to sound misleading. In any realistic future, humans there wouldn't live in Titan's environment. They'd live inside artificial Earth fragments, little pockets of one atmosphere, 1 G-ish simulated by rotation if needed, one temperature range, one liquid water chemistry, parked on Titan's surface or floating in its skies. The moon itself would be more like a location for a complex life support installation than a place anyone truly inhabits. And that leads straight to the next, brutal question. If your real world is a cluster of habitats that must never fail, what does it mean that those habitats sit more than an hour of light time away from the nearest help? When something goes wrong in this sealed ecosystem, there's no quick rescue, no live troubleshooting from Earth, no emergency shipment arriving in days. There is only the people already there, their tools and the clock. Titan's environment is merciless, but its distance is what makes that mercilessness final. You can, in theory, engineer around bad air and brutal cold. You cannot engineer Earth closer. Titan orbits Saturn in a system that sits, on average, about 1.4 billion kilometers from the Sun. Earth and Saturn dance in their own orbits, but when you average it out, the one-way light time between Earth and Saturn hovers around 67 to 85 minutes. That's how long a radio signal takes to cross the gap. That delay quietly kills an assumption we're used to: live help. On the International Space Station, Earth is effectively right there. Ground controllers talk in real time, watch telemetry, catch mistakes before the crew even notices. On the way to the Moon, radio signals take about a second and a half one way. You can still hold a conversation, still negotiate a crisis with half-natural back and forth. On Titan, you send a message and wait more than an hour for a reply. By the time an answer comes, whatever was going wrong has either been stabilized or has cascaded. That's the first big shift distance forces on you. Crisis management can't be a joint activity between the colony and mission control. It has to be local by design. You don't call home to ask, what should we do about this leak? You call home to say, Here's what we did about the leak an hour ago. The people in the habitat aren't just operators, they are the only first responders, only engineers, only doctors, and only investigators the situation will ever have in the time window that matters. Travel time deepens that isolation from a different angle. Cassini, launched in 1997, took nearly 7 years to reach Saturn, arriving in 2004 after complex gravity assist maneuvers. Future human spacecraft will be faster and more capable, but physics doesn't care about our schedules. Titan will always be an outer solar system destination. You don't swing by to drop off spare parts or reinforcements. Every crewed mission is a major expedition with long cruise times, narrow launch windows, and enormous cost. Put those facts together, and the word rescue starts to change meaning. In low Earth orbit, rescue can mean a second vehicle, a quick launch, or at least rapid ground support. At the Moon, it gets harder, but you can still imagine emergency missions on the scale of days to weeks. At Titan, any plan that depends on new people or new hardware arriving quickly is more fantasy than safety protocol. By the time a response mission is ready, launched, and halfway there, the original emergency is ancient history. Psychologically, that level of remoteness isn't just a technical footnote, it shapes how it feels to live there. On Earth, even in remote spots, there's a sense that someone could come if things were bad enough. On Mars, we still talk loosely about rescue missions, even if they'd be difficult. On Titan, you know from day one that help, in the conventional human sense, is never arriving in time. The emotional weight of that is hard to simulate. Every fault, every illness, every argument with a crewmate happens under the knowledge that the circle of people who can do anything real about it is small and permanently fixed. Medical crises sharpen that edge. A sudden stroke, a complicated childbirth, an unknown infection. On Earth, the chain of support runs outward. Paramedics, hospitals, specialists, labs. On Titan, the chain ends at the walls of the habitat. You can send scans and samples back to Earth for analysis, but every question and answer is stretched across hours. There are no medevac helicopters, no transfers to better facilities. The doctor you brought is the best doctor you will ever have, for as long as you're there. The same goes for mental health. Isolation on Antarctic stations or submarines already tests people, even with the knowledge that Earth is under them or overhead. On Titan, home is literally a different region of the solar system. Going outside means a suit, not a coat. Going into town means a pressurized ride, not a walk. There is no stepping away from the mission into a separate civilian world. The mission is the world. This is why outer solar system settlement is not just a farther version of the Old West or a more distant Mars. Frontier stories on Earth always had a thick civilization behind them. Trade routes, shipping, letters, reinforcements, eventual travel back. Titan does not. The latency and the travel time separate it from Earth, not just in kilometers, but in culture. You aren't building a rough extension of human society. You're building a small, sealed fragment and sending it into long-term exile, so failure changes its meaning. On Earth, a failed factory can be retooled, a failed town can be supported, a failed region can be aided by the rest of the planet. On Titan, a failed oxygen plant, a serious reactor fault, or a virulent outbreak inside the habitat isn't a local problem. It's an existential one. The people who are already there will fix it, contain it, or they won't. There is no cavalry. There is no outside world that can pour in resources fast enough to matter. That realization points straight at a deeper, quieter threat than any single accident. Supply. If every repair, every treatment, every upgrade must come from what you already have or from painfully slow, rare shipments, then logistics stops being background infrastructure and becomes the knife edge you live on. And on Titan, that edge is as long and thin as any humans have ever even considered standing on. On Titan, the supply chain isn't background logistics. It is life support in slow motion. When you picture a colony there, you might see domes and reactors and brave crews. What you really need to see is a vast, invisible river of parts, materials, tools and knowledge flowing in from elsewhere, or being rebuilt locally. Cut that river for long enough and the failure doesn't look like a single explosion. It looks like a slow, irreversible slide as one irreplaceable thing after another wears out. Think about spare parts as a form of oxygen. Every valve in the air system, every pump in the water loop, every filter in the CO2 scrubbers, every bearing in a circulation fan has a life. Under Titan's conditions, cryogenic cold outside, warm inside, constant cycling, that life is probably shorter and harsher than on Earth. When the part reaches its limit, you don't get to decide whether to replace it. You replace it or you start a countdown toward a cascading failure. In that sense, a box of replacement seals or a pallet of custom valves is as vital as a tank of breathing gas. Now widen the lens. A durable settlement doesn't just need life support hardware, it needs medical reagents and pharmaceuticals with tightly controlled purity. It needs semiconductors and boards for computers, sensors and control systems. It needs lubricants that still work at the temperature extremes in joints and mechanisms. It needs specialized alloys that don't crack or deform when one side of a structure faces a warm interior and the other faces Titan's deep cold. It needs pressure hull components, cable insulation, radiation-hardened electronics, sterile plastics, glass and composites. On Earth, all of that comes from an insane web of industries, spread across continents fed by global mining, chemistry and manufacturing. We barely see it because it's everywhere. On Titan, you're at the far thin end of that web. If you plan to import most of it, you're accepting that your city is actually more like a glorified research station, always waiting months to years for the next critical shipment. If you try to build it locally, you're accepting something even more daunting. You're trying to regrow an entire industrial civilization from ore and ice and organics in a frozen, distant shell. This is where the phrase local resources starts to mislead. Yes, Titan has water ice, it has nitrogen in the air, it has methane and a zoo of complex organics. That's a better starting inventory than a bare rock with no volatiles at all. But raw materials are only the very first line in a very long equation. Turning frozen crust into surgical steel, or haze particles into clean pharmaceutical precursors, or methane into flawlessly uniform polymers, is a multi-step energy-hungry process that assumes you already have refineries, catalysts, reactors, quality control labs, skilled staff and backup equipment. The moment you write down everything you'd need to manufacture locally, what a city truly uses, from antibiotics to microchips, the picture of a Titan colony shifts. It stops looking like a frontier town with a fusion reactor and some greenhouses and starts looking like a compressed high-tech Earth replica. Mines, smelters, chemical plants, chip fabs, glassworks, machine shops, 3D printing farms, pharmaceutical labs, heavy industry. All of it under or inside habitats that cannot ever lose heat or pressure. That's the real line between an outpost and a home. A scientific outpost can live on disciplined rationing and carefully planned imports. You fly in spare parts. You stockpile meds. You accept that when the mission ends, you leave. A home is different. A home needs to handle people being born, growing up, breaking bones, needing braces, catching viruses, suffering cancers, aging, dying. It needs to fix broken machines that don't care about your launch window. It needs shops that can build the tools you forgot to pack. Titan pushes that requirement to the absurd. It asks you to either accept permanent dependence on an impossibly long supply chain, or to build such a dense, redundant industrial base on site that you've essentially cloned large chunks of Earth's economy under one hostile sky. And all of that must sit at the end of interplanetary routes that take years to traverse and hours even to talk across. Once you feel that, the dream of a self-sustaining colony on Titan starts to wobble. Self-sustaining isn't just about food and air, it's about semiconductors and anesthetics and replacement reactor parts and calibrated sensors. It's about the quiet, unglamorous things that make modern life survivable. Titan doesn't forbid those things physically, but it makes every one of them harder, more fragile and more dependent on an infrastructure that has to be built almost from zero. Yet to be fair, Titan does give one important environmental favour that helps all this machinery survive: radiation protection. Its thick atmosphere shields against a hazard that batters Mars and deep space. That's a real mercy, and it deserves to be recognised honestly. The problem is that even this genuine advantage, when weighed against everything else, still doesn't turn Titan into a place where humans can truly live. It just removes one bullet from a very full chamber. Titan does offer one real kindness, and it's important not to fake that away. While almost everything else about this moon works against human life, its thick atmosphere does something crucial. It shields the surface from a lot of harmful radiation. In that single respect, Titan is kinder than Mars and far kinder than the open void of deep space. On Earth, our atmosphere and magnetic field team up to blunt the constant stream of high-energy particles from the Sun and from distant cosmic sources. Strip that protection away, and you get something closer to what Mars lives with: a thin atmosphere, no strong global magnetic field, and a surface bathed in more radiation than we'd ever accept for long-term human health without heavy shielding. Titan doesn't have Earth's magnetic shield, but it does have a blanket of gas that's even denser than ours at the ground. That blanket matters. A thick atmosphere gives charged particles a lot of material to plough through before they can reach the surface. They scatter, they slow, they get absorbed. For robotic systems, that's already a win. Electronics, sensors, and delicate instruments don't take the same beating they would in an exposed orbit or on an airless rock. For human planners, the implication is clear. If you're going to park habitats somewhere in the outer solar system, putting them under Titan's sky is safer in radiation terms than leaving them hanging in deep space. Spacecraft measurements suggest Titan doesn't generate a strong intrinsic magnetic field of its own. Instead, it sits inside Saturn's huge magnetic environment and develops an induced magnetosphere as the solar wind and Saturn's field interact with its atmosphere. In practice, that means the heavy lifting for surface protection is being done by the air, not by an Earth-like magnetic bubble. Day to day, what matters for you standing on the ground is that there's a lot of stuff above your head to soak up incoming particles. Stack this against Mars and you can see why radiation specialists perk up when they talk about Titan. On Mars, shielding has to come from walls, regolith, water, and clever habitat design. On Titan, the sky itself contributes a big chunk of the protection you need. That makes some engineering problems easier. You can, in principle, spend less mass on overhead shielding and more on other systems. It's not nothing, it's a real environmental edge. But here's the twist that brings us back to the larger argument. Radiation was never Titan's main problem. You can solve radiation with rock, water, metal, clever geometry, and if you really want, simply by going underground. It's a serious issue, but it's also one we know how to engineer around in many locations. Titan's thick atmosphere is a luxury on this axis, not a rescue from its core hostility. Because even with that shielding, nothing else important changes. The air is still anoxic nitrogen and methane that will suffocate you. The temperature is still deep cryogenic, freezing water into stone and pushing standard materials and biology far outside their operating range. The gravity is still so low that long-term human health is a giant question mark. The light is still so weak and filtered that sunlight is basically a rounding error in your power budget. The logistics chain is still stretched across billions of kilometers. The industrial stack you'd need is still enormous. Radiation protection helps you keep your reactors and your people safer from one class of invisible threat. It doesn't help you breathe. It doesn't melt the ice you need to drink. It doesn't magically make hydrocarbon rain useful to crops. It doesn't shorten launch windows or shrink transmission delays. It doesn't give you a local semiconductor fab or a pharmacy or a refinery. You're slightly less threatened by space, but just as threatened by Titan itself. This is where a dangerous mental shortcut tends to appear, mistaking less bad for good. Compared to deep space, Titan's surface is less bad for radiation. Compared to Mars, it's less bad in that one way. It's tempting to let that relative improvement colour everything, to think, well, if we're safer from radiation, maybe this is a friendlier place overall. That's the trap. The body doesn't care that one bullet has been removed from the chamber if 5 others are still loaded. So we should say it clearly and fairly. Titan's atmosphere is a genuine natural asset. It makes robotic exploration safer and, in principle, can ease some design burdens for human habitats. If you had to choose between living on an airless rock in Saturn's radiation environment or under Titan's sky, you would pick Titan every time. But that choice doesn't mean Titan crosses the line into habitable. It just means the baseline is slightly less lethal in one particular way. By now, Titan has been granted its best possible environmental argument, a dense atmospheric shield that really does protect. And still the core verdict hasn't moved. Breathing, warmth, gravity health, energy, logistics, and industrial closure all remain unsolved at a planetary scale. The moon is safer for machines and slightly safer for people inside shells, but it is no closer to being a world you could simply join. That sets up the next phase of the story. If nature won't give us a livable Titan, can engineering brute force one? What if we stop hoping the outside will ever help us, and instead design fully sealed, heated, pressurized cities on the surface? Domes and towers that hold a pocket of Earth in the middle of Saturn's coldest night. The next step is to test that strongest, most straightforward human answer and see whether even that can truly be called living on Titan. Once you accept that Titan itself will never meet you halfway, the most obvious human response is simple. Bring your own world and seal it. Picture domes on the surface or long pressure hulls half buried in the ice. Inside, warm air, liquid water, crops under artificial lights, streets and rooms at shirt-sleeve temperature. Outside, a frozen orange twilight you never have to touch. This is the first serious non-fantastical answer. Sealed surface cities. There are real reasons this idea keeps coming up. Titan's surface pressure of about 1.5 bars means your habitats aren't fighting a brutal vacuum on the outside. On Mars or the Moon, a crack in the hull is catastrophic because the interior is pushing outward against almost nothing. On Titan, the pressure inside and outside can be made closer. Structurally, your domes and cylinders carry less stress. In principle, that could let you build larger, more open interiors without the same risk of explosive decompression. But the moment you relax about pressure, thermal reality slams back in. A sealed city on Titan has to hold an Earth-like interior at, say, 290 kelvins, while the outside sits near 94 kelvins. That's almost a 200 degrees Celsius difference end to end, across every wall, window, joint and pipe. Heat leaks out constantly. Every surface becomes a place where precious warmth flows into the cryogenic night. The bigger you build, the more area you have losing energy, even as more people inside demand more heat. Keeping that interior stable isn't just a matter of cranking up the thermostat. You have to maintain liquid water throughout the entire life support network. Pipes, tanks, recyclers, hydroponic beds, waste processors, all of them must stay above freezing by a safe margin, or ice starts to form in corners, constrictions and valves. Any structural element that lets ice take hold is a future crack waiting to happen as expansion and contraction cycle. Your city isn't just warm, it's full of interfaces where warmth and lethal cold meet, and those interfaces have to behave predictably for decades. Power interruptions, which on Earth might mean a long, miserable blackout, take on a different role here. In a Titan surface city, a serious power loss is a time-limited survival event. The temperature gradient will not wait. Interiors begin to cool. Water in minor lines or neglected spaces starts to freeze. Batteries in unheated compartments sag. Restarting complex systems after a deep chill becomes its own engineering crisis. The city's design has to assume that almost nothing can be allowed to go fully cold without consequences. Now scale up from a tightly managed research base to a place where thousands might live. A small outpost with a few dozen people, nuclear power and strict mission discipline is conceivable. You can track every system. You can schedule maintenance. You can enforce rules on energy use and recycle nearly everything. That already pushes engineering, but it fits inside our current imagination. A city is different. A city means hospitals with intensive care units, schools full of kids, workshops where amateurs tinker, green spaces, entertainment venues, factories, and storage yards. It means people who are not all engineers or astronauts, people who make mistakes, get distracted, have bad days. Every new layer of normal life, sports, art, small businesses, hobbies, adds loads on the power grid, demands on air and water cycles, wear on infrastructure and complexity and governance. Agriculture alone explodes the requirements. Are you growing food in stacked hydroponic farms? You need lights, pumps, nutrient management, pollination systems, monitoring, and a whole human ecosystem of farmers and technicians. Do you import most food instead? That tightens the supply chain noose. Either way, food stops being a simple question and becomes a major branch of industrial planning under Titan's conditions. And floating over all of this is the maintenance burden. Every square metre of hull, every metre of pipe, every joint in the heating system, every scrubber, fan, light, door and cable is aging. In a small habitat, a dedicated crew can stay ahead of that with checklists and careful scheduling. In a city, you need layers of repair crews, inspection systems, spare parts depots, training programs. You need industries that exist purely to keep the other industries intact. Under Titan's relentless cold, nothing is truly low maintenance. When you put all of that together, a sealed surface city on Titan starts to look less like living on Titan and more like parking a piece of Earth on Titan. The environment outside shapes the engineering, but it never becomes part of the human world inside. You're not adapting to the moon, you're walling it off and running an independent biosphere under a shell in which every breath, every sip of water, and every hour of warmth is the product of ongoing industrial effort. That's the hidden question underneath the dome concept. If the only survivable environment is the one you bring with you and keep running at an enormous cost, can you honestly say you're living on Titan at all? Or are you just operating a complex life support vessel that happens to be resting on Titan's crust instead of floating in space? Once that doubt sinks in, the next idea usually appears. Maybe the surface is the problem. Maybe the answer is to go down, into the ice, beneath the crust, toward the hidden water we suspect lies below. Perhaps underground, the temperature swings are gentler, the shielding stronger, the structure's safer. The next step is to test that second answer. Hide beneath the ice and see if the world becomes any more human there. When surface domes start to look like fragile glassware on a frozen anvil, the next idea is to go down. Bury the habitats, carve tunnels, use the ice itself as armour. If Titan's exterior is too exposed, maybe the real refuge is under the crust, where temperature swings soften and the universe feels farther away. And beneath all of that sits the biggest temptation of all, the thought of a hidden ocean. There are solid scientific reasons that vision took hold. Cassini's gravity measurements and Huygens radio data have long pointed to something strange inside Titan, a layer that behaves like liquid water beneath the rigid ice shell. Early NASA interpretations put that buried ocean maybe 55 to 80 kilometers below the surface. In human terms, that's unimaginably deep for drilling, but in planetary terms, it's right under the skin. A whole world with a global salty ocean hidden beneath ice is an irresistible image. Once you imagine that ocean, the story writes itself. Maybe you dig down in stages, building buried habitats along the way. Maybe you tap into slightly warmer layers, using the overlying ice as insulation, until you reach a vast reservoir of liquid water you can use for life support, industry, maybe even far down the line, some kind of exotic ecosystem. The surface becomes just a thin, hostile crust over a more forgiving interior world. But more recent reanalysis, including work published in late 2025, has begun to complicate that neat picture. The data still favour some kind of internal liquid, but it may not be a simple, continuous global ocean. Instead, Titan might hold slushy layers, partial oceans, or isolated pockets of liquid water and ammonia deeper down, closer to the core. Rather than a clean uniform sea, the interior could be a messy stack of ice, slush and scattered reservoirs. For science, that's fascinating. For settlers, it's a headache. Even if the ocean were perfectly global, the depth alone is brutal. Tens of kilometers of ice rock stand between any surface outpost and that liquid layer. We struggle to drill a few kilometers through rock on Earth with a full planet's industry behind us. Doing something even more massive, through cryogenic water ice under 0.14 G with all equipment shipped or built locally, that's not an early phase colonization plan. That's a multi-generation mega project. So most hide under the ice concepts pull back from that fantasy and suggest something more modest. Bury habitats in the upper crust. Dig tunnels and chambers a few meters to tens of meters down. Let the overlying ice provide radiation shielding and some thermal buffering. Maybe integrate your mining operations so that the act of digging for water ice also creates new living space. In principle, this could take the edge off the surface extremes. Burial does buy you a few things. Temperatures underground tend to be more stable than on the surface, especially if you go deep enough that daily and seasonal swings get damped out. Overhead ice can help smooth out micrometeorite risks and shield against any remaining high-energy particles that the atmosphere doesn't already handle. Structures might be less exposed to direct methane rain and surface winds. It's an appealing adjustment, but it doesn't change the fundamentals. The rock you're excavating is water ice at 94 kelvins. Cutting tunnels through that material is not like carving through limestone. Thermal management gets weird. If you warm the walls too much, you risk softening, creep, or refreezing in strange patterns. If you keep them too cold, they remain brittle, and any stress concentration, say from habitat expansion and contractions, can cause cracks. Your excavation gear, your supports, your liners all have to operate in a medium that flips between rigid and plastic depending on small changes you introduce. Meanwhile, everything that matters inside the habitat stays the same. You still need a fully breathable atmosphere, complete life support cycles, and a strong heat budget. The ground around you may drift a little less in temperature than the open air, but you're still raising your living spaces from 94 Kelvin to comfortable room conditions. You're still fighting the same chemical mismatch with the outside. You're still dependent on reactors, recyclers, and carefully maintained machinery. You haven't escaped the machine, you've just wrapped it in a thicker blanket. Industrially, tunneling itself becomes a major branch of the economy. You need specialized vehicles and cutters, dust and chip removal systems, support structures, ice handling logistics, and ways to reinforce or line chambers so they stay stable over decades. Every meter you go deeper adds to the power bill and the maintenance load. Underground habitats may be less vulnerable to surface storms and temperature swings, but they're more vulnerable to geological issues we don't fully understand in this kind of ice rock. And that hidden ocean, the thing that makes Titan feel almost warm under the skin? For now, it remains primarily a scientific treasure, not a civilizational shortcut. It might host exotic chemistry, maybe even prebiotic processes we don't yet grasp. It might tell us how watery worlds form and evolve, but as a practical resource, it is too deep, too uncertain in shape, and too expensive to reach with any near-term or even medium-term technology. You can't plan a settlement around a reservoir you might tap in a century, so the underground option turns into another version of the same pattern. Buried habitats solve some exposures and smooth some variables, but they don't touch the core dependency. Whether you're on the surface or under it, your world is still an artificial bubble running on imported or hard-won power, feeding on carefully processed local material and separated from Titan's native environment by layers of insulation and steel. That brings the focus to a different kind of question. If neither surface domes nor buried tunnels really let humans join Titan's world, maybe the crucial thing to examine is not shelter at all, but supply. Can Titan itself feed a colony's systems with local matter? Can the ice, the nitrogen, the methane, and the organics be turned into the oxygen, plastics, metals, and chemicals a human enclave needs? Or do they just sit there as frozen possibility? If habitats and tunnels can't make Titan welcoming, maybe the planet itself can still help. This is the strongest hopeful case: in situ resource use. Instead of shipping everything across 1 billion kilometers, use what Titan already has. And on paper, this is where Titan finally looks impressive. Start with water ice. Titan's crust is loaded with it. We've already seen that ice as bedrock, as rock under our hypothetical boots. In principle, you can mine that ice, haul it into warm processing units, melt it, purify it, and then split it into hydrogen and oxygen. For a human settlement, oxygen is gold. You need it for breathing. You need it as oxidizer if you're going to burn local methane for power or propulsion. Titan's environment doesn't give you oxygen for free, but the raw H2O is there, locked in the geology. Then there's nitrogen. Titan's atmosphere is mostly nitrogen at a comfortable pressure range. That's not useful to your lungs by itself, but it's excellent as a buffer gas in habitat air. Instead of importing nitrogen to dilute oxygen and keep fires under control, you can pull it straight from outside, compress it, clean it, maybe tweak it, and you have the bulk of an Earth-style breathing mix ready to go. That's a significant win compared with places where you have to manufacture or ship every litre of internal atmosphere. The headline act, of course, is methane and the broader family of hydrocarbons. Titan's sky holds methane. Its lakes and seas are full of liquid methane and ethane. Its dunes are built from more complex organics formed by photochemistry high in the atmosphere and rain down over ages. This is a serious chemical inventory. With the right plants and reactors, you can in theory make plastics, solvents, fuels, waxes, and countless other carbon-based products from what's lying around you. Scientists thinking ahead have already sketched out energy concepts built on these materials, chemical schemes that pair locally produced oxygen with methane, wind power driven by Titan's dense air, hydro-style power using methane and ethane flows, even niche solar plays where you accept terrible insulation and just oversize your arrays. Titan is not like the Moon or Mercury, where you're scrounging for the basics. It has nitrogen, hydrogen, carbon, and oxygen all present in some form, and that's a rare combination. This is the core of Titan's best defense. If any place in the outer solar system can, in principle, feed its own colony, it's a world like this. Ice to crack into oxygen and hydrogen, nitrogen for breathable mixes, hydrocarbons for energy and industry, complex organics as a treasure chest for chemistry. Compared to a bare rock with only minerals and maybe trace volatiles, Titan looks almost indulgent. But there's a gap between useful resources and easy resources, and that gap is where the dream breaks. Every step from raw Titan matter to human-grade product comes with a price. Mining ice in minus 179 degrees Celsius means operating heavy equipment and conveyors in cryogenic conditions, then hauling that ice into heated facilities. Splitting water into hydrogen and oxygen means large-scale electrolysis, or some other energy-driven process. Storing oxygen and hydrogen safely means tanks, insulation, valves, and controls that also have to survive Titan's extremes. Nitrogen from the air still has to be pulled in, compressed, filtered, and blended. Methane from lakes has to be pumped, piped, or distilled. Turning photochemical fogs and organic sands into something like pharmaceutical precursors or structural polymers means multi-stage refining, separation, cracking, synthesis, purification. Each stage needs reactors, catalysts, monitoring, and people trained to run it, all of which themselves depend on imported or locally manufactured hardware. So Titan may be resource-rich, but it's process-poor. The resources are not lying at room temperature on a beach, waiting to be scooped up. They're locked in ice at cryogenic temperatures, dissolved in lakes you can't touch bare-handed, or floating as haze particles in a freezing atmosphere. To get anything human useful out of them at scale, you have to build an entire ladder of industry: mining, transport, primary refining, secondary chemistry, fabrication. That ladder sits on top of a power system that must never fail. And that's the deeper point. A civilization can survive almost anywhere if it can cheaply transform local matter into what it needs. On Earth, we've built that transformation machine over centuries with countless layers of infrastructure and redundancy. On Titan, you would have to bootstrap a similar machine under far worse conditions, with far less margin for error at the far edge of the solar system. So yes, Titan can in principle feed its own colony with air buffer gas, oxidizer, fuel, plastics and more. The chemistry allows it, The raw ingredients are there. But nothing about that process is easy. Every kilogram of local resource you use has a hidden energy bill, a hidden complexity bill, a hidden maintenance bill attached. If those bills ever go unpaid, the flow of materials that keeps the colony alive starts to stutter. That takes us straight into the final decisive question. If the main barrier between Titan's raw inventory and a functioning human world is energy at scale, could we solve that? Could reactors, wind farms, methane plants, and every other trick we know flood the system with enough power to make all these processes routine? Or does the need for colossal, flawless energy just tighten the noose? The next step is to give Titan its strongest possible pro-engineering case and see whether even that can carry the weight. If Titan's big problem is that everything useful sits behind a wall of difficulty, the natural response is to ask, what if we just pay the bill? What if we bring so much power to Titan that all the mining, melting, cracking, heating and recycling become routine? In that story, reactors glow, turbines spin, chemical plants hum, and energy brute forces the world into something we can live with. The starting point for any serious version of that story is nuclear power. Titan's sunlight is a joke, about 1% of Earth's before the haze, maybe a tenth of that at the surface. NASA's Dragonfly rotorcraft doesn't even pretend to use solar. It carries a radioisotope generator because no realistic panel setup could feed a flying lab there. Scale that logic up, and it's clear any human base will be sitting on top of nuclear systems, not solar farms, as its primary heart. Reactors do change the game. A compact fission plant can pump out megawatts day and night, independent of seasons or haze thickness. With enough such reactors, you can melt ice into water, crack water into hydrogen and oxygen, keep whole districts warm, and run industrial equipment that turns Titan's raw inventory into food, plastics, metals, and air. Suddenly, all the energy-hungry steps we talked about, electrolysis, refining, pumping, heating, become technically possible at scale. And nuclear isn't the only card on the table. Titan-specific studies have pointed out a menu of secondary options. You could tap chemical energy by burning local methane with locally manufactured oxygen. You could explore hydrogenation pathways, combining hydrogen from ice with organics to create different fuels and chemicals. You could harvest wind energy, that dense atmosphere, even moving slowly near the ground, carries significant kinetic energy that big turbines might capture. You could set up hydro-style systems where methane and ethane flow through channels, driving generators like cold rivers. Even solar, despite everything, might play a niche role if you accept huge arrays feeding low-power systems. This is Titan's strongest engineering defense. It is not resource empty. The world is full of matter you can, in principle, turn into energy or energy carriers, and energy you can turn into matter you need. Give a well-supplied team a few decent reactors and a couple of decades, and you can imagine a tight but functioning industrial ecology rising out of the ice and orange haze. But there's a difference between possible power sources and civilization-grade reliability. Keeping a probe alive on tens or hundreds of watts is one thing. Running a settlement, truly running it, means continuous heat for habitats, oxygen production, water processing, food growth or synthesis, transport systems, communications, medical gear, and heavy industry. It means backup capacity for when something breaks. It means margin for unexpected loads, a disease outbreak, a damaged reactor, a bad batch of parts that has to be replaced early. At that scale, power management isn't just have a reactor. It's an entire grid with redundancies, storage, distribution, and careful load balancing. It's spare parts for the reactors themselves, control rods, pumps, heat exchangers, shielding elements, electronics. It's inspection teams, repair crews, training programs, safety protocols. Every piece of that depends on the same supply and industrial systems we already know are stressed to the limit by distance and environment. And the more power you feed into Titan's machine world, the more tightly human life gets bound to that machine. Big reactors make it easier to keep the inside warm, which makes it easier to expand, which makes the colony more dependent on uninterrupted energy. You chase comfort and scale by building a bigger and more complex life support engine, and then you have to keep that bigger engine running flawlessly in a place that punishes every maintenance slip with ice and darkness. There is one quiet benefit. With enough power, you can use heat itself as a tool. You can keep larger buffer volumes warm so that short outages don't immediately freeze pipes. You can preheat external equipment, thaw stuck lines, keep emergency shelters live. Thermal inertia becomes part of your safety net. In that sense, energy doesn't just run machines, it thickens the margin between normal operation and catastrophe. But even an abundant, well-managed power grid doesn't touch two of Titan's hardest limits. It does not reduce the distance to Earth. Every spare reactor's part, every kilogram of enriched fuel, every rare dopant or catalyst you can't yet make locally still has to crawl across the outer solar system on slow ships. And it does not change human biology. You can pump as many megawatts as you like into heaters and centrifuges. The surface gravity will still be 0.14 G, the outside chemistry will still be anoxic and cryogenic, the psychological weight of distance will still be there. So the fair verdict on the power solves it argument is complicated. Enough energy can, in principle, overcome many of Titan's individual obstacles. It can melt the ice, split the water, warm the domes, run the greenhouses and fuel the factories. It can make survival for a small, disciplined, highly technical population feasible for stretches of time that look impressive in mission planning documents. What it cannot do is change the nature of the relationship between humans and Titan. Even in the best-powered scenario, you are still living inside an engineered island, suspended in an environment that never helps you directly. More energy makes the island bigger and more comfortable, but it doesn't turn the surrounding sea into land. In fact, the more you rely on high-density power systems, the more disastrous a serious failure becomes. That realization pushes the discussion into its last, strangest phase. If Titan cannot be made human by tweaking shelters, exploiting resources, or piling on power, maybe the only way left is to stop trying to fit humans to Titan at all. Instead, we fit machines to Titan, or we fit humans to machines. Floating habitats, robotic surrogates, heavy augmentation, artificial gravity, solutions that start to sound less like colonization and more like rewriting what living there even means. When ordinary engineering runs out of answers, the ideas that are left stop looking like colonization and start looking like science fiction. Titan is exactly the kind of world that forces that shift. Its atmosphere and gravity practically beg you to think in extreme directions. If we can't live on the ground, maybe we live in the sky. If we can't send vulnerable bodies, maybe we send machines. If unmodified humans can't cope, maybe we stop insisting on unmodified. The first wild idea is aerial living. Titan's air is dense, its gravity is low, and we already know from Dragonfly that flight there is almost easy compared to Earth. So people start sketching floating stations, giant blimps filled with warm gas, aircraft-like habitats cruising lazily through the haze, mobile sky cities that simply never touch the frozen, hazardous surface. In that vision, the ground becomes irrelevant. You live perpetually aloft, above the dunes and lakes, but look closely and the same constraints appear again. An aerial habitat still sits in an atmosphere with no oxygen. Its hull still separates warm human spaces from cryogenic nitrogen methane air. Every cubic meter inside must be heated, pressurized and supplied with processed air and water. The lift gas might be heated nitrogen or hydrogen rather than helium, but you still depend completely on power and maintenance. Wind patterns, while gentle near the surface, can be ferocious higher up. You gain mobility and maybe a bit of insulation. You don't escape the life support cage. The next idea is more grounded and frankly more credible. Let the robots take the hit. Titan is almost perversely well suited to machines with rotors, wings, wheels or even legs. Low gravity, thick air, reduced radiation, abundant interesting chemistry, This is a robot heaven. Instead of filling Titan with fragile, fully biological humans, you fill it with drones, crawlers, burrowing probes, floating labs. They do the exploring, the sampling, the drilling, the hazard work. Humans in that framework step back. Maybe a tiny, heavily protected crew lives in a compact habitat, controlling and supporting a whole ecosystem of autonomous machines on the surface. Maybe further in the future those machines evolve into largely independent systems, with human operators sitting safely on Earth, guiding major decisions with the long communications delay built into their procedures. In that version of settlement, the things truly engaging with Titan's environment aren't people at all. They're metal and code. If you're determined to put more human into the mix, the conversation eventually drifts toward modification. Titan doesn't just ask for a better coat, it asks for permanent artificial atmosphere, permanent artificial heat, perhaps even artificial gravity if you want long-term health. Once you're leaning that hard on technology, it's a short conceptual step to say, maybe the humans themselves change. Heavier reliance on implants and prosthetics, bodies that spend most of their time connected to support systems, genetic tweaks to cope, even slightly, with low gravity or constant indoor life. That's where things get philosophically strange. If you need artificial G from rotating habitats, machine-mediated breathing, full environmental control, and maybe even direct neural links to robotic surrogates to function, what exactly are you adapting to? At that point, the architecture isn't adapting to humans. Humans are adapting to a machine architecture. Titan is just the address where that architecture happens to stand. One more extreme route tries to separate Titan from Titan's surface entirely. Instead of living on or under the ice, you build large rotating habitats in orbit around Saturn or Titan, huge wheels or cylinders that spin to provide close to 1G with Earth-like environments inside. Titan is then just a nearby destination. Robots drop down, work and rise back up. People live in artificial gravity with normal air and temperature, visiting the moon by proxy. In that scheme, around Titan might someday be plausible as a human neighbourhood. On Titan still is not. Notice what's happened to the meaning of living there in all these escape routes. Floating cities never touch the ground. Remote presence keeps real human bodies far away or in tiny isolated shelters. Heavy biomechanical mediation turns settlers into long-term patients of their own life support technology. Rotating habitats that make sense biologically don't need Titan at all. They could orbit anywhere you can find sunlight and raw materials. Every path that looks like it might rescue the dream of Titan as a human destination does it by quietly removing the on-Titan part, or by transforming human into a tightly coupled component of a machine system. The more seriously you try to solve Titan, the more the solution walks away from the original picture of people building cities on an alien shore. That's the edge of the mystery this whole argument has been driving toward. When all the reasonable and unreasonable fixes are laid out, the last thing left to decide is what we actually mean by living on Titan. Is a research outpost enough? A robotic empire run from Earth? A network of sealed machines with a few humans inside? Or does living there require something that Titan, even with all our tricks, will never give? By now, the pattern is impossible to ignore. Everything that first made Titan sound promising turns out to be a trick. Dense air, lakes, weather, low radiation, easy flight, the headline features that keep it in best colony sites lists, do not add up to a human world. They add up to a world that is perfect for robots and profoundly wrong for us. Start with the checklist that actually matters for an open human planet. Breathable oxygen in the environment. Titan fails completely. Its air is nitrogen and methane with essentially no free oxygen. Tolerable temperature range? Titan sits at about 94 kelvins, roughly minus 179 degrees Celsius. So cold that water is bedrock and normal biology is frozen out of the landscape. Gravity that we know can sustain long-term health? Titan's 0.14 G is below even the moon's, with no evidence it can keep bones, muscles, hearts, or developing children healthy over a lifetime. Sunlight strong enough to support cheap, simple energy and maybe agriculture? Titan gets about 1% of Earth's sunlight before the haze cuts it down again. On top of that, the logistics are brutal. Titan lives in the Saturn system, with one-way light time on the order of more than an hour, and travel times measured in years. Supply chains never really close. Rescue is not an operational category. Any serious reactor part, medical breakthrough, or missing specialty material has to crawl in from the inner solar system, and every delay stretches over terrifying distances and times. So Titan fails as an open human world in every essential sense. You cannot walk into its air, you cannot drink its rain, you cannot farm its soil in any normal way. You cannot count on its sunlight. You cannot trust its gravity. You cannot lean on its distant, strangled connection to Earth when something large goes wrong. It withholds all of the background gifts that make Earth feel effortless. That does not mean Titan has no human future at all. A robotic future there is basically guaranteed. Dragonfly is already the opening move, a nuclear-powered rotorcraft custom-built to ride Titan's dense air and low gravity. More drones, more landers, more orbiters will follow. The conditions that betray us, cryogenic cold, thick atmosphere, weak sun, are almost ideal for hardy machines that don't breathe, don't mind low G, and can sip power slowly for years. A human scientific foothold is also not forbidden by physics. With serious nuclear power, tightly engineered habitats and disciplined crews, you could run research bases on or under Titan's surface. People could spend months, maybe years working there, then rotating back home. Think Antarctic stations with more distance, more machinery, more risk and more reward. In that narrow frame, temporary, elite, fragile. Living on Titan, in the everyday language of space missions, is possible. What collapses under scrutiny is the stronger claim that humans could live on Titan in the planetary civilizational sense, that they could build cities that rely on the landscape the way cities on Earth rely on rivers, soil, air and sun, that children could run under an alien sky that protects them, that a culture could emerge which feels native to Titan instead of permanently strapped to an artificial fragment of Earth bolted onto Titan's crust. At best, what the physics allows is the sealed industrial enclave, a machine world powered by reactors, feeding on mined ice and processed hydrocarbons, staffed by people who never truly meet the outside except through thick glass and pressure doors. Everything vital, air, water, warmth, gravity simulation, medicine, manufacturing remains inside the system. Titan itself supplies raw chemicals and a place to stand. It never becomes home. That's the real verdict this whole argument has been driving toward. The right conclusion is not Titan is impossible in the narrow engineering sense. With enough money, reactors and courage, you can put humans there and keep them alive for a while. The conclusion is that Titan is impossible as a human world. It cannot, even in principle, offer the open, forgiving partnership with life that we implicitly mean when we talk about living on a planet. And here is the final twist. That's exactly what makes Titan so scientifically important. It sits in a razor-thin band of possibility, close enough to Earth in some ways to tempt us, far enough in others to betray us. It has air but not breath, rivers but not water, seas but not oceans we can join, chemistry rich enough to hint at prebiotic steps but not compatible with our form of life. It is a case study in how a world can almost work for us and still fail in every way that matters. Titan is not a second Earth in waiting. It is a magnificent false promise, a place that pulls human imagination forward only to force us to sharpen what we really mean by habitable, livable, and home. We will send machines there. We may send people there. We will learn extraordinary things there. But the only way to live on Titan is to not live on Titan at all, to live inside machines that refuse as long as they can to let Titan in. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.